Visual Riddles is a benchmark designed to test the capabilities of large vision and language models in interpreting complex visual scenarios, requiring common sense and world knowledge. The benchmark comprises 400 visual riddles, each featuring a unique image created by text-to-image models, question, ground truth answer, textual hint, and attribution. Human evaluation reveals that existing models lag significantly behind human performance, with Gemini Pro 1.5 leading at 40% accuracy. This underscores the potential of Visual Riddles as a valuable resource for enhancing vision and language models' capabilities in interpreting complex visual scenarios. The benchmark's main task involves solving riddles in an open-ended visual question-answering (VQA) format, which evaluates the ability to detect subtle visual cues and apply common-sense reasoning or world knowledge to formulate answers. Additional tasks include a multiple-choice version of the main task, allowing for easy automatic scoring based on accuracy, and assessing the ability of models to determine the accuracy of open-ended responses in two settings: reference-free and reference-based. Experimental results reveal a significant gap in performance between humans and state-of-the-art vision language models. Surprisingly, the multiple-choice format proved almost as difficult, with performances slightly superior to those in the open-ended task, but with notably high performances when auxiliary data is included. Automated tests, both reference-free and reference-based, show that Gemini Pro 1.5, the top autorater, matches human judgment 87% of the time in reference-based evaluations, proposing a suitable method for evaluating open-ended answers. The findings suggest that the Visual Riddles poses a significant challenge even to state-of-the-art vision and language models, emphasizing the critical need for further developments in common-sense reasoning and world knowledge integration to improve model performance on complex visual riddles. To support future research and model evaluation, the Visual Riddles dataset, code, and leaderboard are made publicly available at https://visualriddles.github.io/. This research paper presents a comprehensive analysis of the Visual Riddles benchmark, which is designed to evaluate the capabilities of vision and language models in solving complex visual riddles that require common-sense reasoning and world knowledge. The benchmark includes 3 tasks: open-ended visual question answering, VQA, multiple-choice VQA, and automatic evaluation of open-ended VQA. These tasks are intended to assess models' abilities in locating visual clues, integrating them with common-sense reasoning and world knowledge, and formulating coherent and correct answers. The authors introduce several state-of-the-art vision and language models that are evaluated on each of the tasks in the Visual Riddles benchmark. They describe the experimental setup and results of each task, including the impact of auxiliary information such as textual hints and source attributions on model performance. The study also categorizes the instances based on the type of common-sense reasoning and knowledge required, including safety-related knowledge, biological knowledge, cultural knowledge, and more. The Visual Riddles benchmark is hand-curated by 7 designers experienced in generating images with text-to-image models. Each riddle consists of a synthetic image paired with a question and a corresponding ground truth answer. Designers had access to advanced text-to-image models and were encouraged to embed cultural nuances and their own world knowledge into the riddles. The images were not only photorealistic but also contained all necessary elements to lead to the correct answer. In conclusion, this research paper provides a detailed overview of the Visual Riddles benchmark and its potential to evaluate the capabilities of vision and language models in solving complex visual riddles. The findings of this study contribute to the development of more advanced models capable of integrating visual information with common-sense reasoning and world knowledge. The research paper presents a comprehensive evaluation of various vision language models on the Visual Riddles benchmark, a challenging open-ended visual question-answering task. The task requires models to solve riddles based solely on accompanying images, and the authors assess the performance of humans and models on this task. The evaluation process involves collecting human responses to the riddles through crowdsourcing on Amazon Mechanical Turk, where annotators provide justifications for their answers and are encouraged to use tools like Google Lens and search engines to research clues. The authors also extract open-ended answers from various vision language models, including large vision and language models and caption generation models. The correctness of human and model answers is assessed using a multiple-choice selection format, where 3 annotators select responses that match the ground truth without any hallucinations. The results show that models face significant challenges in solving the riddles, with the best-performing model, Gemini Pro 1.5, achieving a score of 40%, while human performance reaches 82%. The authors also evaluate the performance of models on a multiple-choice VQA task, where each riddle includes an image and a question with 5 answer choices. The results indicate that this task is comparably challenging to the open-ended visual riddles, with GPT-4, Gemini Pro Vision, and Gemini Pro 1.5 showing the highest accuracies. Furthermore, the authors investigate the capability of vision and language models to accurately judge the correctness of open-ended answers to visual riddles through automatic evaluation experiments. These experiments are critical for identifying the most effective approach for automated evaluation and supporting scalable future work on the benchmark. Overall, the results highlight a recognition gap between human and model performance, indicating that current models still struggle to solve visual riddles accurately. The authors provide detailed results and analysis on various categories and difficulty index levels, as well as annotation guidelines and results. The research paper presents a comprehensive evaluation of various autorator models in assessing open-ended answers to visual riddles. The evaluation is conducted in 2 scenarios: reference-free and reference-based, where models are provided with or without ground truth answers, respectively. The results show that Gemini Pro 1.5 achieves the highest performance in both scenarios, with an accuracy of 52% in the reference-free context and 87% in the reference-based context, as measured against human ratings. Utilizing Gemini Pro 1.5 as the optimal autorator, the paper evaluates various models on 3 open-ended settings, including the main task, hint-assisted, and attribution-assisted variants. The results suggest that models perform better when provided with hints but struggle with attributions, highlighting the challenges in improving models' visual reasoning capabilities. The paper also explores 2 key aspects of the visual riddles challenge: assessing models' use of visual cues through comparisons between original and modified images, and examining generative models' efficacy in replicating images aligned with the riddle prompts. The ablation study with modified images reveals that models struggle to identify correct answers, especially with modified images, and have a high gap between original and modified images. Gemini Pro 1.5 excels with a 60% gap, indicating its ability to identify correct answers despite changes in critical image elements. Furthermore, the paper presents a unique challenge posed by the visual riddles prompts to text-to-image models. The results show that popular open-source diffusion models struggle to reproduce visual riddles, with only 12% of generated images successfully matching the prompts. The most successful model, SDXL Turbo, achieves a 15% success rate. The low overall success rate underscores the unique challenge presented by the visual riddles prompts, establishing them as a valuable resource for evaluating and advancing text-to-image generation. Here is a combined summary of pages 9 and 10 of the research paper. The paper discusses the Visual Riddles Challenge, a novel benchmark for evaluating the common-sense reasoning capabilities of multimodal models. The challenge involves interpreting complex visual scenarios that require nuanced understanding of visual cues and world knowledge. The authors highlight the close relationship between their research and common-sense reasoning in multimodal models, as well as the evaluation of factuality in both language-only and multimodal settings. Recent progress in vision language models has sparked interest in common-sense reasoning, leading to complex visual reasoning challenges within the vision and language domain. The authors mention specialized tests for understanding associations and analogies, interpreting unusual images, visual abductive reasoning tasks, multimodal humor understanding tasks, and world-instructed image editing tasks requiring common-sense reasoning. The paper also discusses the evaluation of factuality, which has been a focal point in language-only models, particularly for tasks where outputs rely on grounding texts. The authors mention reference-based metrics, such as Rouge, Blue, and BERT score, as well as reference-free metrics, like Summa C, Q2, and FIC. Parallel advancements in vision language tasks have introduced metrics such as ClipScore, AviBench, and TIFA, with benchmarks like milebench, see true, blink, and vibe eval enhancing the rigor of factuality assessments. The Visual Riddles Challenge offers a uniquely stringent test of multimodal model capabilities, requiring both deep world knowledge and nuanced common sense reasoning to interpret complex visual cues. The authors acknowledge that their dataset, although smaller than other benchmarks, was meticulously annotated to ensure a rich and diverse set of common sense challenges. They also acknowledge potential limitations, including the use of generative tools, which might introduce inherent biases, and the possibility that individuals may find certain riddles offensive despite efforts to prevent this. The paper concludes by highlighting the performance gap between state-of-the-art vision language models and human performance, underscoring the ongoing challenge of bridging human and machine understanding in complex visual interpretation tasks. A promising future direction is to explore model performance across multiple images generated from the same prompt, allowing for a more robust evaluation of visual reasoning capabilities. The pages discuss various research papers focusing on high-resolution image synthesis, visual language models, and evaluation metrics for text and image generation. Key contributions include improving latent diffusion models for image synthesis, introducing progressive adversarial diffusion distillation, and proposing new benchmarks for evaluating visual and language understanding. The papers also explore the importance of common sense in visual reasoning and the need for robust evaluation metrics that can assess the factual consistency of generated text. This appendix provides essential insights into reproducibility, encompassing detailed explanations and examples regarding model evaluation, analysis, and data collection. The Visual Riddles dataset is accessible on Hugging Face, along with comprehensive information about dataset fields and loading instructions. The authors executed all evaluation code on a single Colab notebook, accessible on their website. For models using APIs like Gemini and GPT-4, they employed CPU resources, while for models like Java and InstructBlip, which required GPU resources, they utilized a single A100 GPU. They utilized a paid plan for models with APIs, enabling them to generate 400 predictions for each task within a timeframe of less than 30 minutes. Equivalent to the runtime of Java and InstructBlip models used locally with GPUs. Table 6 lists the models specified in the APIs and how they were used. The authors extracted textual content from web page URLs using Selenium WebDriver for visual riddles containing attribution fields, resulting in lengthy prompts. The Visual Riddles benchmark was created by 7 experienced designers who generated images using text-to-image models. The annotators were instructed to create images that integrate information with world knowledge and common sense to answer a given textual question. The answer must be grounded in the data presented in the image, making it impossible to respond accurately without comprehending the image and identifying the embedded clues. The designers used advanced text-to-image models, including Midjourney, Ideogram, Canva, DALL-E 3, and Stable Diffusion, to generate high-quality images. Each image must be sufficiently challenging such that at least one of the evaluation models fails to correctly answer the question based on the provided image. The designers provided not only the correct answer to the question but also a hint to the image that should guide where to look in the image when trying to solve the riddle. Figure 6 depicts a heat map showing how models and human annotators failed to solve visual riddles in the Visual Riddles dataset, visualizing by the color intensity of each cell. The z-axis represents different categories of riddles, while the y-axis shows the difficulty index levels. Red cells highlight particularly challenging areas, with vertical red bands indicating categories that consistently pose difficulties and horizontal red bands confirming the appropriateness of the difficulty index levels assigned. This visualization underscores the diverse range of common sense knowledge needed to effectively tackle the visual riddles. This research examines the performance of vision and language models on the Visual Riddles Challenge, focusing on the correlations between model failures and human failures across various categories and difficulty levels. The analysis identifies model weaknesses in categories such as object counting, temporal principles, and physical principles, with human performance on physical principles being particularly susceptible to errors. The heat map in Fig. 6 illustrates the distribution of model failures and human failures across different categories and difficulty levels, highlighting the most demanding elements of the benchmark. The distribution of categories and difficulty levels is presented in tables 7 and 8, respectively. The categories include cultural principles, social norms, and safety and survival, among others, while the difficulty levels range from 0, least difficult, to 3, most difficult. The results show that models and humans struggle more with higher difficulty instances, emphasizing the need for improvement in these areas. The research also explores different prompts for various models, including multiple-choice VQA, VQA automatic evaluation, and auto-rater for open-ended VQA. The prompt structure is outlined in tables 9 and 10, respectively. The ablation study investigates whether models base their answers solely on text or consider visual clues, using the same prompt structure as in table 10. To evaluate human performance on the Visual Riddles challenge, annotators were recruited through Amazon Mechanical Turk, paying $18 per hour. The guidelines for human annotators involved a qualification round, where they reviewed task guidelines and solved 5 riddles of varying difficulty. The assessment of their responses and feedback enabled the selection of qualified annotators for the task. The research discusses the annotation process for visual riddles, focusing on personalized feedback and the evaluation of human and model answers. Annotators were presented with guidelines and examples, including Fig. 7 and Fig. 8, which demonstrate the need for common sense and world knowledge. The UI page for annotation, as shown in Fig. 9, was designed to facilitate the process. For evaluation, the mTurk platform was used, paying annotators $18 per hour. The process included a qualification round and personalized feedback, resulting in 10 candidates proceeding to the actual annotation phase. During annotation, each annotator was provided with the image, question, and correct answer, along with candidate answers from models and humans. The guidelines emphasized accurate answers without hallucinations. The cannot determine option was frequently selected by models, indicating hesitation. However, providing hints and attributions reduced this hesitation, as seen in Table 11. This process and its outcomes are crucial for understanding model performance in visual question answering tasks. In Table 12, we observe the performance of various models in excluding cannot determine answers, with Gemini Pro 1.5 achieving a 48% accuracy without hints and 74% with hints. GPT-4 shows promising results with 52% accuracy without hints and 71% with hints. The LLAV models, A1.634B and A1.57B, demonstrate lower accuracy rates. The Visual Riddles prompt set, presented in Table 13, highlights the struggle of text-to-image models in generating images that match the given prompts. SDXL Turbo 18 is the best-performing model, achieving a 15% success rate in generating images that fit the Visual Riddles prompts. In the discussion on potential negative societal impacts, it is noted that visual riddles may inadvertently reinforce biases and could potentially disadvantage users with specific cognitive or sensory impairments. To address these issues, a continuous review process involving diverse stakeholders will be conducted to identify and mitigate any biases or exclusions. This process will also involve refining the riddles and improving the evaluation methods. Figure 8 illustrates the guidelines for mTurk annotators for solving a visual riddle as an open-ended question. It includes a question, answer, explanation, and notes on why the answer is correct, as well as attribution for the image, indicating when world knowledge is required and suggesting a Google search for data. The figures and guidelines presented on pages 21 and 22 of the research paper detail the process of annotating visual riddles for a machine learning task. Figure 9 illustrates an example of the Mechanical Turk (mTurk) user interface page used by annotators to answer questions given an image and a question. This interface is crucial for collecting high-quality training data for visual question answering models. Figure 10 showcases the guidelines provided to mTurk annotators for evaluating different answers to the visual riddle. The annotator UI page displays the visual riddle, the correct answer, and several candidate answers. Annotators are tasked with identifying which candidate answers correctly solve the visual riddle, providing detailed reasoning for their decisions in the explanation and notes section. These guidelines ensure that annotators understand the criteria for correct and incorrect answers, enabling them to accurately label the data. This labeling process is vital for training and evaluating visual question answering models, as it directly impacts the model's performance and ability to generalize to new, unseen data. The use of mTurk for data annotation allows for large-scale data collection with minimal cost and time, making it an efficient method for gathering diverse and challenging visual riddles. By leveraging human intelligence through crowdsourcing, researchers can create robust datasets that help advance the state of the art in visual question answering.